This set of videos is about linear equations, and when we say linear in the context of differential equations, we mean linear in the dependent variable. Here we see a form of an equation a1 of x dy dx plus a naught of xy is equal to g of x. One thing we can take from this is that the coefficient functions a1 of x, a naught of x, and the function on the right, g of x, at most depend on x. They could be constants or they could be expressions involving x, but not y. So we see that y appears as the function itself and its derivative, and nothing more interesting than that. We can put this into standard form by ensuring that the coefficient on the highest derivative term, in this case dy dx, the first derivative, is 1. And so we have dy dx plus p of x times y is equal to f of x. When we know a differential equation is linear, then there's a pretty straightforward path that we can use to solve it that I'm going to illustrate using this example. Consider 3 dy dx plus 12y is equal to 4. We have constant coefficients, but the dependent variable y appears as nothing more interesting than itself times 12 and then its derivative times 3. Putting it into standard form, we've divided by 3 and we have dy dx plus 4y is equal to 4/3. I'll give you the start to finish process later. For now though, I'm just going to show you how it works. If we multiply both sides by e to the 4x, then what we get is e to the 4x dy dx plus 4e to the 4xy equals 4/3 e to the 4x. I'm multiplying both sides. Before I continue with this, I'm actually going to take a little aside here. Let's see what happens if we differentiate e to the 4xy with respect to x. Well, this requires a reminder. So we're going to have a second aside. So we can consider implicit differentiation. You may recall something in maybe first semester calculus, something that looked kind of like x squared y cubed plus 4xy squared is equal to 5. For our purposes right now, I'm just going to focus on this first term, x squared y cubed. Differentiating x squared y cubed with respect to x, assuming that y is a function of x, requires the product rule. So we have 2xy cubed plus 3x squared y squared, but since we're differentiating y, but with respect to x, we need to throw in a dy dx or y prime because of the chain rule. Applying that to our first aside, the derivative with respect to x of e to the 4, I put 4x up there, e to the 4x y, I put e to the 4y up there. Of course, I meant e to the 4x. If we differentiate e to the 4xy with respect to x, we have the first times the derivative of the second, so e to the 4x, and the second is being differentiated with respect to x, so e to the 4x dy dx. And then the derivative of the first times the second is plus 4 e to the 4x times y. You may note that's exactly what we had after we multiplied both sides of the equation by e to the 4x. Thus, what we get on the left-hand side after multiplying by e to the 4x can be interpreted as the derivative of the product e to the 4x times y. So, the equation that we have, e to the 4x dy dx plus 4e to the 4xy equals 4/3 e to the 4x, can be written as the derivative with respect to x of e to the 4x times y equals 4/3 e to the 4x. Where what we've done is interpreted the left-hand side as the derivative of a product. This is going to now be solved by integrating both sides with respect to x. On the left-hand side, the integral of the derivative, well, that cancels each other out. We end up with, e to the 4x times y. On the right-hand side, we're integrating 4/3 e to the 4x. We'll divide out the 4 because of a du thing. Remember the substitution rule. And on the right-hand side, we have 1/3 e to the 4x plus our constant of integration. And then to solve for y, we simply divide both sides by e to the 4x. And with that constant, I'll actually write it as multiplying by e to the negative 4x. We were able to do that because we multiplied both sides by e to the 4x. The natural question is, where did e to the 4x come from? Well, for the equation in standard form, dy dx plus p of x times y is equal to f of x. I'm going to put a star next to that because I'll reference it later. Suppose we have some function mu of x, this is the Greek letter mu, such that when we multiply star by that function of x mu, we get mu dy dx plus mu times p of y is equal to mu times f of x. So in the previous discussion, the mu was e to the 4x, right? If it happens that d mu dx is equal to mu times p, then the left-hand side becomes mu dy dx plus d mu dx y, and I don't need the right-hand side. And what we've just done is replaced mu times p using what we suppose would be d mu dx. Then what we have on the left-hand side would be something like a mu prime y plus mu y prime, which is a derivative with respect to x, assuming mu and y are functions of x, of mu times y. So we have this differential equation, the left-hand side of which looks like mu dy dx plus d mu dxy. That's replacing this left-hand side here, and we can rewrite the left-hand side as the derivative with respect to x of mu times y. The right-hand side is mu times f of x. Again, recognizing the left-hand side is the derivative of a product. Obviously, we need to know what mu is. Well, to find mu, we used the assumption that we made d mu dx is equal to mu times p, where p was present in the standard form of the equation. And that equation, d mu dx is equal to mu times p, is a separable equation. So d mu over mu is equal to p of x dx. I'm throwing in the argument for p so that you know it's a function of x. And we solve separable equations by integrating. So the natural log of the absolute value of mu turns out to be the integral of p of x dx, which then gives us that mu is equal to e to the integral of p of x dx. Now, in case you're wondering about the absolute value, now technically this would be the integral of p of x dx plus c, right? Well, that plus c, we've already seen how to deal with that before, would actually give us mu is equal to, say, like an e to the c times e to the integral of p dx. And then we could say, well, that e to the c is really just a constant, so I'm just going to call it a whole different constant, and then the plus or minus gets rolled into that c, but none of that actually matters because remember what we did. We multiplied both sides by that mu. If there was a constant c inside of mu, we would have that constant in every single term. It would end up dividing out. Therefore, we actually don't need even the constant of integration in this case. And so we have that mu is equal to just that e to the integral of p of x dx, and that thing is called an integrating factor. And good news, we never need to use a constant of integration when we have an integrating factor.